This is the 5th section of chapter 1 on algorithms, and this is on bin packing algorithms. So first of all, what is a bin packing algorithm? Well, these are algorithms that allow us to put different size items into what we call bins, so that there is the least amount of wasted space and the least number of bins used. Now, these are used on things like production lines, where maybe they order objects of a certain size, maybe in certain lengths, and then they need to be cut into different size lengths, and they don't want a lot of wastage. It may be placing files on a hard disk so that the files are placed in the most efficient way using the least space possible, or even packing items into a lorry. If some, like a big company, has got lots of different size boxes, they need to pack onto a lorry. They want to find the most efficient way to pack them so that they don't have a lot of wasted space and they don't need to use a lot of lorries. Now, when we do these types of problems, we want to know whether we've actually got the most efficient solution. Have we got the least number of bins? So we want to know something called the lower bound. Now, the lower bound will be the least number of bins that this problem could actually be solved with, although that may not necessarily be a solution. So I'll just write that down. So the lower bound is the least number of bins required for packing. Bins required for packing, although this lower bound may not be achievable. So although this may not be achievable. So let's say, for example, I've decided that the lower bound for a problem is 10. I need 10 bins. Doesn't mean I can actually get 10. If I get 10, then it's what we call an optimal solution. So if solution for the number of bins equals the lower bound, I know I've got an optimal solution, but that may not be possible. So it may be, for example, that I get a lower bound of 10, and actually I can only solve it by using 11 bins, for example. Doesn't mean the answer is wrong. Lower bound just tells us the minimum that it could be, but it may often be higher than that minimum. But if we get that minimum, we know it's an optimal solution. So how do we calculate the lower bound? Well, it's the total size of all the items divided by the bin size. Now, this is going to give us a number. Sometimes it gives us an integer, sometimes it doesn't. But whatever type of number we get, we always need to round up. Always round up. Yeah, so even if you got something like 3.1, you'd round it up to 4. So round up to next whole integer. So let's look at these different bin packing algorithms, how they work, and what's the advantages and disadvantages of each type of algorithm. Right, so the first one we're going to look at is what we call the first fit bin packing algorithm. This is how it works. We take each item in the order it is given. We place it in the first available bin in which it can fit in. And the advantage of using this is it's easy to implement. It's not difficult, but it's not likely to lead to a very good solution or an optimal solution. So this algorithm is what we call the first fit decreasing algorithm. Now, the only difference between this and the first fit algorithm is the first step is to sort the items into descending order first, and then we apply the first fit algorithm. So there's this extra step before we use it. The advantage is that we usually get a good solution, a better solution than the first fit, but it may not be an optimal solution. And the last type of bin packing algorithm we're going to be looking at is called full bin packing. Now the way this works is that you inspect the items that you've got, you look at them, and then you put together, pair together, or put 3 or 4 together the items that will completely fill a bin. So let's say, for example, you had a bin size of 20 and you notice that you've got an item of 14 and 6. You put those together to completely fill a bin. Then any items that are left over that you can't put together to completely fill a bin, these are placed in bins using the first fit algorithm. So we go back to this algorithm to place the remaining items. Now the advantage with this type of bin packing is usually to get a good solution. However, disadvantage is it's difficult to implement, especially if you've got a lot of data items, because having to inspect them manually to see which ones fit together to fill a bin, it is going to be difficult and time consuming. Okay, so we've got 9 boxes of fixed cross section, have heights in meters as follows. They are to be packed into bins with the same fixed cross section and height 2 meters. Determine a lower bound for the number of bins needed. So the calculation is going to be the total size of all the items. Now this size might be weight, it might be height, it might be length. We just need to find a total, so we add those together, and then what we do is we divide that by the size of each bin, and each bin is 2. So the top adds up to 8.5. We divide that by 2, that'll be 4.25. Now remember, we always round up, so we'll round up to 5. So this tells us that the lower bound would be 5 bins. And if we found 5 bins, that would be an optimal solution. Or we would know it's an optimal solution if we got 5. Okay, so we're going to use the first fit algorithm to pack the following items into bins of size 20. State the number of bins used and the amount of wasted space. Okay, so the way I'm going to answer this is I'll write the bin number here. I'm not sure how many bins I'm going to use, but let's go to 4 for the moment, might need more. And then beside it, I'm going to write down the items that I'm going to put into that bin. So the first fit algorithm means you start from the left, you work your way to the right and fill a bin as much as you can, and then go back to the start again. So as we use items, we'll mark them off. Okay, so I can get item A in each bin. Remember, each bin has a size of 20. So I can get item A in there. And then item B, because that's 7, so that's now 15 of the 20 used up. So we'll cross these off. So what happens now with the first fit is you skip items which don't fit. So 14, 9, 6, none of these are going to fit. The next one that fits is the item G. That will now take the bin up to size 20. So this bin is now full because we've used a full 20 on that one, so we'll cross off that. And then we go back to the start again. Okay, so what can we get in there? We can get item C, which is 14, so we'll cross that off. Now, what's the most we can fit in that? 6, so we'll put E in there. So item E goes in, that's 6. So this bin is now full. We've used the full 20, that bin. Okay, so bin number 3. So we go back to the start again. So we have to start with the D, that's 9. Okay, then the next item is going to be, I have to use F. So you've got to use the first item that fits. And that's 9. That leaves 2 left. Now if I go across the list, there is no item of size 2. So this bin isn't full. I'm only filling up to 18, so I've got 2 size of wasted space. Okay, so we'll go on to the next one, which is going to be H. We have to use H, the first item that's available that can fit in the bin. So H, there is no item of size 5, so I have to stop there. So this one is not full, there's 5 left. Or shall I write down that I've used 15? Let's write down at the size how much space is wasted. So 2 here, 5 here. So we're now on to bin number 5. So we cross off 15. Now we go on to I, which is 6. We can get that in there. We can get J in there. That's going to be 7. Whoops, I'm problems writing J's today. I, J. So that gives me 13. So I can get those 2 in. Problem is you cannot fit K in there. So this has used 13. So we've got 7 of wasted space. So we have to go onto a 6th bin. And that will just be K on its own. So that uses 8, which means that there's 12 wasted space in that bin. So you can see that 6 bins are used. 6 bins are used, and the amount of wasted space is going to be those numbers added up together. So that'll be 2 plus 5 plus 7, that's 14, plus another 12, so that's going to be 26. Now it doesn't say what those are, meters or anything like that, so we'll just put 26 units. Yeah, because we don't know what those units are. So you'll notice this is the same data that we used in the previous example, but we're going to be using the first fit decreasing algorithm to the data. So the first thing that we need to do is to sort the data into descending order, starting with the largest item first. So that's going to be H, which is the 15, then C, which is 14. What comes next? I can see I've got F is 9, and so is D. That's also 9. The order in which we put those two, that doesn't matter because they're both the same size. We've got A and K are both 8. A is 8. K is 8. So I'll cross those off. We've now got the items of size 7, which are B and J. And then we've got 2 of 6, E and I. So E and I. And then lastly, we have the G of 5. Okay, so now we've got these in order of size. We now apply the first fit bin packing algorithm. So that means going from left to right and putting the items into the first bin they can fit in. So I'll do H first. Let's cross that off. And then the next item that fits, completely fills the bin, is going to be G. So H and G go in the first bin. Okay, there's no wasted space there. So what I'll do now, I'll only write down at the side what wasted space there is. So this one's going to be 0. Right, go back to the beginning of the list. So first fit, so we have to use the C first. Then we find the next item that will fit into that bin. So that's going to be E because of the order I've put them in. So E is going to go here. So no wasted space in that bin. We go to the third bin. So we'll cross off the C there. So first fit means we put F in, then we put D in, that fills the bin. There's no other item that's going to get in this. We've got 2 units of wasted space. Then the next one's going to be A that we have to use. So A and then K. There isn't any item of size 2, so A and K will get used. Then we're now onto a 5th bin. So we have B, which is 7, J, which is 7. We've got 6 units of space left, so we can fit I in there. And this bin will be completely full. So B, J and I, which means now we've used all of the items. Notice, compared to the previous one, we only use 5 bins and there is less wasted space. Now I just need to correct a mistake here. That's not 2 units of wasted space because that's 16, so that's 4 units of wasted space. So I'll write down wasted space is 2 plus 4, 6 units, and 5 bins are used. So 1 less bin and less wasted space. Okay, so we've got these items here. They're going to be placed into bin sizes of 25. Part A, we want to determine a lower bound for the number of bins. So a lower bound is going to be the total of all the item sizes divided by the bin size, and that number rounded up to the next integer. So it's going to be that sum, whoops, let's try that line again, divided by 25. Okay, the top adds up to 111. We divide that by 25. Now that gives us 4.44. So we now need to round that up. So a lower bound is going to be 5 bins required. Now we're going to apply the first full bin algorithm, which means having to look manually, inspecting the items. Are there ones we can put together to make 25? Okay, well, A, B and C can be put together to make 25. So A, B and C is 25, so that would fill a bin. Now we've got the 11 here and 14, right, so E and J will make 25. So E and D and J will make 25, 11 and 14, so D and J, that's 25, so we'll cross those off the list. Then we've got 13 and 12 makes 25, so E and I is 25. Now that's it. It doesn't matter how you try and pair or put 3 of these together, you cannot make them get 25. Right, so we can start to do this. So bin number 1 is going to be A and B and C. So here we've got a full bin, so there's no wasted space there. I'll just put 0 down. Bin number 2, again no wasted space, so D and J, so D and J. Full bin, no wasted space, so let's put 0. Bin number 3, again, is going to be full, so 13 and 12 is 25, no wasted space. And then for the remaining items, we use the first fit algorithm. So the remaining items are the 17, so F. So cross that off and see if there's any items. The first item to fit into it is going to be G. So that now takes it up to 21. There's no other items of that are going to fill that bin. They're too big. So this has 4 units of wasted space. And then this one looks like the last bin. That's going to be H and K. So that makes 15. So that will give 10 units of wasted space. So we have 14 units of wasted space using 5 bins. Part C asks, is this solution optimal? Give a reason for your answer. Well, it is optimal because the number of bins used is equal to the lower bound. Okay, so the solution is optimal. Since the number of bins used equals the lower bound. Okay, so a plumber needs to cut the following lengths of copper pipe. All these lengths are in meters. The pipes come in lengths of 2.5. Calculate lower bound for the number of pipes used. So this is a bin packing problem. So to find the lower bound, it's going to be the total length of all the items. So we'll add all of those together. And then we'll divide by the bin size. Now in this case, the bin size is the length of the pipe. We want to cut these lengths of pipe. We want the minimum amount of wastage. So this is a practical problem. Well, all of maths is very practical. So we'll divide that by 2.5. Okay, so we're going to get 9.7 divided by 2.5. Let's work that out. And we'll get 3.88. So remember, you round it up. So our lower bound for the number of pipes needed is going to be 4. Lower bound is 4 pipe or 4 lengths of pipe needed. Right, part B. Use the first fit decreasing algorithm to determine how many lengths of pipe may be cut from, or how many required lengths may be cut from 2.5 meter lengths. So if it's first fit decreasing, the first thing we need to do is to put these in order of size. So I can see the longest there is C, which is 1.4. So I'll just write the letters down rather than the lengths. And then E, which is 1.3. Then D. And then I've got 0.9s. So we've got F, H, and J. F, H, and J. There aren't any other 0.9s. The rest are 0.8s. So A, B, G, and I. G, and I. Right, so we've put them in order of size. The next thing we need to do now is to place them in bins. Now each bin or each pipe basically is 2.5 meters. So we just place each one in the first bin available. So I probably need to rub these out so I can see what the sizes are. Right, so C goes first, that's 1.4. Now are there, how about E? E is 1.3. That won't fit, that will make 2.7. D is 1.1. Yes, that will work. So D 1.1. So that gives a full bin with no wasted space. Right, we go back to the start of our list again. So we're going to have E, which is 1.3. So we've used that. Then we go to F. F is 0.9, so that will fit fine. So F 0.9. That is going to give us 2.2, so there aren't any other items that are going to fit into that. So if we've got 2.2, then we're going to have 0.3 meters of wasted pipe. So we now go on to H, and H is 0.9. The next one in our list is J, and J is 0.9, so that will fit. So that's now 1.8 meters used, so we'll just cross that off. Now will A fit? A is 0.8. Now A won't fit. In fact, we will need a length of, if it's 1.8, 0.7, and there are no lengths of 0.7. So this bin or this pipe has been used. So that will give us how much? 1.8, yeah, 0.7 meters of wasted pipe. We'll go on to our fourth one. So we now need to start with A. A is 0.8, so we'll cross that off our list. B is also 0.8, so that will fit, no problem. That gives us 1.6 meters. So will I get G in there? So G is also 0.8, yeah, that will fit. That will take us up to 2.4 meters. So that actually means there's only 0.1 meter of wasted pipe. And then we need a fifth pipe. And that's going to be the length I on its own, which is 0.9. So 0.9, which means the amount of wasted pipe is going to be 0.6 meters. 0.6. Okay, so our solution is going to be 5 pipes, and we will have 0.7, 0.7, 1.4, 1.7 meters of wasted pipe. Okay, we'll move on to part C, and part C says use full bin packing to find an optimal solution. So this will just be a little bit more tricky because we've got to try and find lengths of pipe that fit together to fill a bin. So let's start with the easy one. So those two, C and D, are going to make one pipe. So I'll just put C and D there. No wasted space. Any others that go together? Now I know the 0.8s, two 0.8s make, or three 0.8s make 2.4. So two 0.8s and a 0.9 is going to make 2.5. So A, B and F will do. So A, B and F, there's going to be no wasted pipe there. Okay, let's see what else we've got. And we've got two more 0.8s and a 0.9. So G, H and I. So let's put those down, G, H and I. Again, no wasted space. Now that leaves E and J. and we just use the first bin packing to fill those. There's only 2 and they're going to fit together. So I'll just put E and J. That will make 2.2, so we'll have 0.3 of wasted space. So using the full bin packing, actually find an optimal solution. I know it's an optimal solution because it's 4 pipes with 0.3 meters of wasted pipe. So since the solution is equal to the lower bound, I know that this is an optimal solution. So I could even write down that this is an optimal solution because it's the same as the lower bound. So you should now be able to do exercise 1E on pages 20 to 21. So just a recap of the different bin packing algorithms and their advantages and disadvantages. So make sure you know how to use the first fit algorithm, the first fit decreasing algorithm, and the full bin packing algorithm, which does require you to use the first fit algorithm for any items that can't be placed together to completely fill a bin.